Hello, this is our presentation in busbar manufacturing. We are Group 4, and my teammates are Sabino Rodriguez, Danny Ventura, Harry Chang, A. Aaron Caprino, and Jose Garcia. So our focus production is on making busbars for Tesla electric vehicles, as the current busbars are, cheap. Tesla's our target, but busbars are widely used in different electrical devices. And when I say widely, I really mean widely. Busbars allow us to distribute electrical power through multiple connections. A simple example of a busbar that you might see in everyday life is a power strip.
Okay, so right now we're just gonna kind of go into the background of what our project is based off. So first of all, Tesla bus bars are usually metallic bars used to connect high voltage equipment at electrical switch yards and low voltage equipment to battery banks. Tesla bus bars are mainly used to distribute power from a supply point to a number of outputs. Ideally, bus bars want to be made out of copper, but you can use other materials when trying to factor in things as cost. Current Tesla bus parts do cut corners to reduce prices by using cheaper materials and using inefficient welding methods, causing impurities within the metal welds. On the other side, if you decide to use bus bars, quality bus bars, they tend to be too expensive due to the material, which is copper. So the problem that we're facing is that Tesla bus bars lack quality due to manufacturers keeping the cost down. Bus bars are made of cheaper materials such as aluminum, result in weaker structural support and less electrical conductivity. The key thing about using aluminum is the weaker structural support. Weaker structural support means that bus bars need to be replaced more often, and the bus bars require more maintenance. In the long term, this extra required maintenance and replacing the bus bar does lead to higher maintenance costs.
So during the initial concept phase, as a team, we all got together and brainstormed some different ideas and just trying to understand how to create a robust, high quality, long lasting product. So the first thoughts that initially came through our heads was, how do we increase the efficiency during this whole concept phase? We've done a lot of background research already previously on friction stir spot welding. So we have a general idea of how it affects welds. And we also gathered information from a lot of the research that we've done on automation as well, and in a smart factory setting. So we started putting all these things together and started getting an idea of putting together a smart friction stir spot welding automated factory. So once we got all that information brainstormed in our heads, now it's coming down to conducting the initial tooling design. Friction stir spot welding is using materials that are non-consumable tools, and we actually research different geometries as well to try and understand how to best optimize our process. And also on top of that, we actually integrated different types and research different types of automation robots to use within our assembly. And friction stir spot welding reduces waste, so it's actually a sustainable product that doesn't use gas or any filler material. Next. And then on top of that, we moved into the development phase. So we understand that Tesla is projected to manufacture about 500,000 electric vehicles for fiscal year 2020. During the calculations, that it requires about 225 bus bars per vehicle, which requires about 112 million bus bars for just 2020 alone. That's a lot of bus bars that we need to understand how to try and manufacture. So during the development, we had to understand, hey, how do we create an assembly line that is a smart factory that is going to be able to drive on its own, utilizing lights out manufacturing. So we started taking and research ABB and KUKA robots, which is actually some of the robots that are driving the wave. It's the wave of the future. We know that conducting one weld is going to take 10 seconds with copper and aluminum welding. So doing a couple more calculations that It requires about 4 of these machines in order to produce about 2.5 million bus bars that we need to do for the month. 9.5 million bus bars we need for the month. And then on top of that, we have to mount sensors to stream data in order to upload to the cloud assembly, so we can utilize our machine learning program to run the right regression so we can build better models each time. Utilizing conveyor belt system as well, and a laser cutter and an automated packaging system. During the development phase, so we actually mapped out the whole development phase. It goes from the start, from receiving to the conveyor belt, to a laser cutter, to the friction stir spot welder, to the quality inspection point, packaging, shipping, to the end product, which is where our customer is going to be.
So with that, we go into the prototype phase. And for us, in order to really understand, we have to understand that the prototype should represent the actual and the future product. So that being said, we have to present Tesla a product that they are going to like and that is going to represent what we're actually going to sell them, in order for us to catch their attention. Our prototype has to show durability, since the current bus bars that Tesla is using are weak, as it was stated before. They have to be weather durability to extreme cold temperatures, so Tesla can move into that market where they're able to sell, in a lot of places where extreme cold does happen, since bus bars do tend to fail at different temperatures, and also hot temperatures, since we know that some areas here in California do tend to get a little bit hotter than regular Bay Area temperatures. So with that, we go into the launch phase, and for us, it's a little bit different. For our launch phase, technically for our launch phase, you will have to do a bunch of promotion and marketing strategies and stuff like that. For us, our launch phase was a little bit more focused to a specific company that we wanted to target. So it was more of a sales team's focus and to the specific customer. Once we could get Tesla interested in our product, that's already a win situation, since we are making these bus bars specifically for them. So that's technically our launch phase kind of idea. And since Tesla does sell their cars, with the idea of them being environmentally friendly, we could sell our bus bars as kind of going along with that same ideology, where they're environmentally friendly, since they're better. There's no fumes, so they're not harmful to any humans and all that.
So next we move to the manufacturing phase. As mentioned before, there's approximately 230 to 250 bus bars in a Tesla vehicle. So that's approximately 9.5 million bus bars per month that needs to be created at the factory. So the estimated Tesla vehicle production per month was 33,400. So a copper piece for the bus bar and aluminum is usually created via an extrusion method. Then after that, the bus bars are then bonded via friction stir welding, either traversed or spot welded. Each bus bar is tagged with a RFID code, so that the smart factory could monitor where it's being tracked within the facility, if it's at the beginning stage or at the end stage. Then we move on to the distribution slide. So in distribution, we have packaging, transportation, and delivery. At the packaging stage, it's basically the bus bars are packaged and coated with a corrosion film, which could be removed before being placed in the vehicle. Desiccant packs are used to prevent any possible corrosion in the while transport. Transportation, there's 3 options: air, railway, and waterway. For air, it's usually the quickest option to transport the product from overseas and such. Railways in between for the two, which depending the circumstance, they have to transport aluminum or copper pieces over a few states. They could transport that way, and the slowest method being waterway from overseas transport. So once the creation of once it's transported, it's delivered to the Tesla facility, as seen on the right, where at the Fremont facility, they normally spot weld the two extrusion bars. Then the bus bars are completed at this stage. So there's a wide variety of use for bus bars. Specifically in Tesla, they're using them for the electric batteries from bonding the cells to a bus bar via fuse wire. You see them at the Tesla charge stations where you're transferring high current from high 220s to the plug outlet. As well as like welding systems that you find at Tesla factories for bonding the frame structures, network equipment for low band to avoid low bandwidth within the facility for the smart factory, and cell communication within the facility. There's less interference when you use a bus bar.
So servicing these bus bars aren't really meant to be a non-serviceable item, because to weld them, you have to have a large amount of force. But generally, if a component fails, the only option you have is to replace it. But with the way that these bus bars are assembled, the weld strength is actually higher than the material strength, so the material would break first. Depending on the design of and how everything is built together, a tool designed by NASA to use on the ISS can be used to actually rework these pieces if access to the battery pack is provided. The picture is showing two different tools designed by NASA through a public competition, and those were the final results. So to dispose of the bus bars or recycle them, the material, being copper and aluminum, are both indefinitely recyclable. The only thing that has to be taken into consideration is separate processing for the intermetallic compound created at the weld. There's no filler materials, so it's only pure copper and pure aluminum being processed. If the battery pack were to fail, for example, but the bus bar is still fine, a working bus bar can be taken out of a failed unit and put into one that needs a new unit, instead of having to rebuild a complete other unit or assembly for it.
So in conclusion, there is a market needed to produce better bus bars. As you can see, Tesla, as we said, their bus bars are cheap and they are prone to failure. Producing bus bars with friction stir welding could lead to high tensile strength and better conductivity with aluminum copper bus bars to make them a little bit more affordable, since copper is expensive, but you combine the both, they could be better and more affordable. Our bus bars are environmentally friendly, no toxic fumes at the time of assembly of the bus bars, and they're easily recyclable. Our main target is Tesla companies, but if they find themselves using our bus bars due to higher quality and nearly at the same price as other competitors. So with that being said, if Tesla likes our bus bars, we could potentially move into other markets or other industries with our bus bars, thus creating a higher income in our side. And these are some of our references. Any questions, concerns? And that's the end of our presentation. Thank you.